done all the groundwork for one of us to just pick the rigidity problem and solve it and move on to better things.
I hope so. So yeah, so I'm going to talk about certain approach to rigidity that Alex Samorodnitsky, Ilya Shkredov, and myself have been pursuing for a while. So so let me start with the definition. So let's say that I have a square matrix over some field, and I say that V is rigid with some parameters R and D. If for any other matrix V prime of the same dimension, such that for every I'll say what I mean by that. So here by Vi, I denote the ith row of matrix V. So I say that matrix V is R, D rigid if whenever I take a matrix V prime, that in every row differs from matrix V and in most D coordinates, the rank of matrix V prime is at least R. So that's the definition of R, D rigidity. So in a slightly different form, this definition was given by Boolean in 1977. And the reason he was interested in this was the following result of his. So the following lemma that he proved. For any, let's say, omega n to the epsilon rigid matrix V, the linear transformation that takes x in f to the n and maps it to V times x, also in f to the n, does not have a linear circuit of linear size and logarithmic depth. So Vedant observed that this property, which is very easy to explain to someone who has no computer science background and is not interested in computation, so that this very clean concept, in fact, can be used to prove certain kinds of circuit lower bounds that we don't know how to prove. So so since then, for almost 40 years now, this has been a great challenge to come up with this method, to come up with explicit rigid matrices. Because if you can come up with one, then you get a lower bound for a certain explicit function. So it's a function with many inputs and many outputs, and the circuit is linear, and yet that would be a great result. So so since then, people have been trying, and they haven't accomplished that much. So Vedant asked for rigidity with these kind of parameters. So we want linear remaining rank, and we want n to the epsilon changes in every row. So on the other hand, random matrices are even much better than that. So in fact, over any field, if you look at a random matrix, then you get much stronger parameters. In particular, you can get something like, say, 0.99n and omega n. So this is what you get from random. So you can get remaining rank to be as close to n as you like, and you can get the number of changes per row to be in fact linear. And if we ask, so where are we in terms of explicit constructions? So the best explicit constructions that we have so far. So let's say that we again ask for the 0.99n. So here I would ask, I guess many people in the audience know the state of the art, but so would anyone want to guess what is the best number that we can put here? more guesses. So it's less. It's less than log n. It's less than 2. No, it's 0. So there isn't an explicit. We don't know how to construct a square explicit matrix over any field, where if we change one entry per row, the remaining rank would be 0.999. We don't know. So this, I mean, it's not. I don't know how many people have tried. So I have tried. I know there are a few others who have tried to look at like this particular very narrow question. We don't know. So it is 0. So also, I mean, I think it's remarkable that the gap between random and explicit here is just, it's maybe one of the worst in all problems that I'm aware of. So at the yeah.
In the first place, why do you only care about rows? Why not say that you subtract? You change stochastic basically.
Yeah.
The columns are also only d for every column.
Yeah. So in fact, Valiant, when he defined it, he talked about the total number of changes in the matrix. He said that you change up to n to the 1 plus epsilon elements in the whole matrix. But if you look at his reduction closure, it's enough to constrain the rows. I'll constrain the rows because, in fact, for the approach that I'll be trying, it's important that you constrain the rows.
And it doesn't help you if you say that every column is also bounded by d.
I mean, no. You're so in terms of constructions, no. I'm not aware of any construction where that would make a difference. So yeah, if you can do something non-trivial, assuming that, that would also be great.
Assuming what?
So
you also have bounded on the distance of the columns.
But there is, like I said, I mean, the two questions are equivalent. If you bound the total number of changes by nd, or bound the changes every row by d, the question of finding an explicit matrix is the same. Just changes between n and n over.
yeah.
So there's no difference. I think for the challenge you mentioned at the end, I mean, I also thought about it for a while, and then a couple of years ago, I realized that one reason it's non-trivial is that as the Mount matrix over the reals, you can change one entry per row and get the rank down to n over 2.
Yeah. So somebody.
Something that was not obvious to me for not 25 years before, but it's sort of.
Yeah.
It's obvious, but it's.
I guess, yeah. So someone whom maybe you told it to me. So now I know that Hadamard is not a candidate here. But yeah, I mean, and yet, I mean, random do that.
Maybe a candidate.
No, not for this one. Not yeah.
Oh,
Not for this one. Yeah.
Not for this one.
Not for this one. So good. Okay. So yet, of course, there are some results. So if you ask about 0.999, then it's pathetic. If we allow ourselves somewhat lower rank, then there are some results. So, and the best explicit results that we have are of the form r n over r log n over r. This is assuming that r is not too small, so r is at least a log square then. So over infinite fields, this is due to Spielmann, Shokrolahi, and Stemmann from around 97. And there is essentially the same bound can be proved over finite fields also. This is due to Friedman. So okay, so what is that? Well, so if you insist that r is linear, if r is omega n, then we'll get some constant here. So n over, so that will give us some constant. So and let me say also a few words about the proof technique. So I won't show that argument. It's fairly simple. So basically, the way one proves it over infinite fields is just saying that, okay, so let me look at a square matrix where every minor is full rank. So there are such explicit matrices when the field, I mean, you don't even need infinite field. You just need the field size to be larger than n. And you can, so Cauchy matrix would be like that, say. So you can have a matrix where every minor is independent of size. Every minor is full rank. And then how do you prove rigidity? Well, you say that if there are up to so many changes per row, so then you can use standard results in combinatorics saying that, well, if there are only so many changes per row, then there is going to be a square minor that is not going to be touched. You can get a lower bound for that. And that's the lower bound for the rank of the matrix after changes. That's how you prove a result like that. So that's what what we can call an untouched minor barrier. Untouched minor. Well, it's not a barrier in a sense, but that's some bound. So untouched minor. So you cannot do the same argument, say, over f2, but then there is a different argument that gives essentially the same parameters. Barrier. So, and this is where we are. So quantitatively, this is the best known. So this untouched minor argument. Yep.
Probably one should mention Zarankiewicz just for the untouched minor.
Yeah.
Because that's a technique. And
yep.
another comment is that the full rank minors, or minors being full rank, is not enough in the sense that for the lower bound, in the sense that there are matrices like that which do have linear size circuits of operating.
True. Yeah. So that's in Valiant's original paper. Yeah. So, but in quantitatively, I mean, this gives this bound. It's very weak. That's the best we have. So, okay. So now let me say a little more about Valiant's paper. So Valiant actually he posed some conjectures saying that. So I mean, it's easy to conjecture that some matrix is rigid, and he made some conjectures. So over infinite fields, he said that you can look at the Hadamard matrix, and it's going to be rigid with this omega n and to the epsilon parameters. And over finite fields, he suggested to look at matrices that arise from geometric designs. So let me say a few words about this. So well, really, he talked about f2. So he talked about infinite fields and Hadamard, and then he said that over f2, you can look at geometric designs. Sorry?
Just for the 0.99.
Yeah. So what is geometric design? So okay, so let's look at some large finite field FQ, and let's look at some m-dimensional projective space over FQ. So how many points do we have there? Well, so the number of points would be so q to the m plus 1 minus 1 over q minus 1, which is roughly q to the m. So that's also the number of hyperplanes. And then, okay, so how many points is there on a hyperplane? So, well, again, that's easy to compute. It's q to the m minus 1 over q minus 1, q to the m minus 1. And then if I take two hyperplanes, so how do they intersect? So any two hyperplanes in projective space intersect in the same number of points, and that number, again, one can compute. I can go over this. So, and that's roughly q to the m minus 2. So, and one can, okay, so we have this projective space, we have hyperplanes and points, and we can look at a square matrix, which is just the incidence matrix of hyperplanes and points. Right, so that would be a square matrix. Its size would be n by n. If I look at every row, then there would be W1s. And if I take any two rows, then they would share exactly lambda. There would be exactly lambda points that belong to both rows. So this is the design property. So I have a square matrix of size n by n. So it's a binary matrix, zeros, ones. So in every row I have W1s, and if I take any two rows, they share exactly lambda. There are exactly lambda coordinates where both of these rows have a 1. So let me denote a matrix like that by G M Q. So this is an incidence matrix of a geometric design corresponding to m-dimensional projective space over a finite field FQ. So, and in his paper, Valiant actually made the following conjecture. So that so he said that, well, so matrices he singled out for some reason G2. So conjecture. Valiant 77. Matrices G2Q are omega n to the epsilon rigid over F2. So either he was not writing it, I mean, either he was unaware of some prior art, or he was just too sloppy on stating it, because taken literally, the conjecture is actually incorrect, and there have been earlier results that he could reference and see that, in fact, some of these matrices are just low rank. So They look very nice, yeah, but so in fact, so these are matrices of geometric designs. So apparently, in design theory, people have studied them quite a lot, and in particular computed their ranks over all fields. And and so here is the formula for the rank. So the rank. So let me do the rank over F2. So from now on, I'll be focusing on F2 in general. So this is the field over which I want to study rigidity. The F2 rank of GMQ is the following. So it's n if well, let me not write the precise expression. So it's at least n minus 1 if q is not equal to 2 to the e, and it's actually m plus 1 raised to the power e if q is equal to 2 to the e. So so apparently the rank of this apparently the rank of this matrices is very sensitive to how the characteristic of the field that underlines the projective geometry relate to the characteristic of the field over which you are computing the rank. So if both fields have the same characteristic, so if both of them say are of characteristic 2, then the rank is pretty low. So what is this expression? But if the characteristics are different, then the rank is almost high. It's usually high, so sometimes it's n minus 1, usually it's m n. So okay, so what is this quantity? So what is that? So and we are usually thinking, okay, so we need to fix some asymptotics. We are thinking of m as fixed. We need an infinite family of matrices, and we think of q as growing to infinity. So then this m to the e plus 1. So how does that behave? So well, so we have our n, which is roughly q to the m, right? So which is 2 to the e to the m. So then what is m plus 1 to the e? Well, that's 2 to the e log m plus 1, which is n to the log m plus 1 over m. So this is n to the log m plus 1 over m. So the rank can be pretty low. So it's well, yeah. So these are our matrices. So apparently for design matrices, sometimes the rank. So usually, if the characteristic of the field that underlies the projective geometry is not 2, the rank is almost high. But if the characteristic is 2, the rank can be very low.
I think what Valen meant is the rank over F2 and Q is a prime, and that's a family.
Very plausible, yeah.
Yeah.
Yeah. So in that case, yeah, the paper, I mean, the paper just says that, and yeah. So so yeah. So these matrices, I mean, one can, but on that, I mean, so yeah, he might have. I don't know what he had in mind, but on the other hand, I mean, kind of, one can believe that the reason to look at these matrices is that they have this nice combinatorial structure, and one can hope to use combinatorial structure to prove a rigidity result. So, but the combinatorial structure doesn't change when you change the characteristic of the underlying field. I mean, they're still designs, no matter what is the characteristic of the underlying field. They still have all these nice intersections.
Maybe we're going to mention it, but maybe not. But the combinatorial, the structure of the combinatorial design, the small intersections, can play a big role in a proof, and the field matters. So we have this paper with Zev and Amir and Boaz about exactly these matrices. So the matrix of the projective plane, but you take the rank over the reals, and not only are the rank full, but it remains linear if you change n to the epsilon of the entries, as long as you change the one entry arbitrarily on the reals. So it's some kind of a monotone rigidity result. If you change, in fact, just little root n, there are root n ones per row. If you change little
Mhm.
every row,
Mhm.
as long as you change once to something else as opposed to zeros.
Mhm. Mhm.
Then because of the geometric intersection property,
Uh-huh.
the rank remains linear.
So, but I presume that the characteristic of the field over which you define the geometry doesn't doesn't play a role at all.
No, it's good.
Yeah, that's.
The proof works over the reals.
Yeah, yeah, yeah.
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 So,
Mhm.
but
Mhm.
yeah. So, no, I understand your point. I'm just saying
Uh-huh.
that the geometry can play a role when you take into account the characteristic of the field, as in this background. In fact, the result holds for.
Oh, no. But that's a different field that you are talking about. I'm talking about the field that underlies the projective geometry, and in your paper it does not play a role.
No, it doesn't play.
Yeah. So that's.
Yeah. So, so you are saying when.
I'm saying that, yeah, so that, I mean, one could think of variance conjecture as being based on the intuition that I mean, these designs, they have nice combinatorial structure, and that structure should imply rigidity. So it shouldn't. It shouldn't, just because there are, some of them have, combinatorial structure is the same, but just the rank is low to begin with. So, yep.
So, just trying to get the asymptotics here. So m is fixed, so n to the log m over m is some small constant, right?
Yes. Well, yeah.
So it's like, let's say n to the 0.1 or something.
Yep.
So why is just the rank being sublinear is a barrier to proving rigidity?
Well, it's a barrier to proving this form of rigidity. So if you want omega n into the epsilon rigidity that Boolean asks for to get circuit lower bounds, well, I mean, if your rank is sublinear, then you cannot prove an omega n rank lower bound.
Okay.
So that's even with no changes. That, yeah.
Okay.
So, okay. So, but that was just kind of going over the state of the art. So the thing that we want to pursue is actually proving rigidity of these matrices, of these matrices, despite the fact that some of them are of low rank. So rather than trying to shoot for this omega n into the epsilon regime that we have no idea how to approach, we'll set ourselves a more modest goal. So we'll try, so our goal, so we want to prove some result of the form, we want to prove that, well, that these matrices, say, G, M, Q, are, well, n to the 1 minus 2 epsilon, 1 plus delta, n minus 2 epsilon rigid for some epsilons and deltas. So this is what we want to prove. So this, I mean, if we could prove that, so this wouldn't be a rigid result strong enough to get circuit lower bounds, but that would already be far beyond this untouched finite barrier technique.
It also has applications.
It also has applications, yeah. Not as grand as those ones, but there are applications.
Other low bounds that we don't know.
Yeah.
For example,
In communication complexity.
Yeah.
prove low bounds in communication.
Yeah, it would separate the
hierarchy.
communication complexity variance of the polynomial hierarchy and business.
Yeah. So and we won't prove that. So but this is our goal, and we'll make some steps towards there, hopefully. And also, so one thing to mention here is that, so when I talk about these geometric designs, so they have a clean definition, right? So I take, there is some finite field, the projective space, but one can also look at combinatorial designs with parameters of geometric designs. So this one can denote by VM. So VM is just a square matrix of size n by n with, so let me put it informally, with the same intersection properties as GM for some Q. So these are combinatorial designs, and in fact, what I'll be doing, I mean, since I only am going to only use the combinatorial structure, so that whatever I say would also apply to, in fact, all combinatorial designs. So I'm not going to use anything more than combinatorics. And so let me mention one last thing here. So there is this old conjecture in design theory, in fact, even older than Boolean's paper, by Noboru Hamada, saying that if we just, although for geometric designs, the rank is well understood, so you can compute it over any field, there is a closed form expression. If you say that you don't have a combinatorial design, but you don't have a geometric design, but you have a combinatorial design with the parameters of geometric design, and then you can ask, so what is the rank? And Hamada's conjecture says that, in fact, the rank would always be at least as high as for geometric designs over any field. So yeah, and that's open since early 60s, I guess, maybe if not late 50s. So yes, so.
The parameters there, the upper bound in the case of best characteristic is something like n to the epsilon, where you should for a rank lower bound of n to the 1 minus epsilon. Like you want it to be.
Sorry. It should be exactly. I mean, so the sum should be just slightly above 1. Yeah. So that. Sorry. Yeah. Yeah.
So probably you said this in the first 10 minutes, but there's geometric designs and combinatorial designs which are obtained by the point line incidence properties. Is that?
So geometric designs are the ones that are obtained by hyperplane point incidence properties, and then combinatorial designs is just a broader class of designs. It's just a square matrix with the same number of ones per row, same intersection properties. But you can get them from other processes. You don't have to.
They need not be like some underlying geometry.
Yeah, there need to be an underlying geometry. Then you can ask about the rank. And this question about the rank, I mean, it's pretty important for if you want to prove a result like that. You first need to be able to prove non-trivial lower bounds on the rank of these objects, and that's exactly the Hamada conjecture. So in fact, yeah. So since if one try to exploit only the combinatorial properties, then one has to go through Hamada conjecture first. So okay. So that was the general introduction. So let me start saying something about what we actually do. Well, so as in any rigidity proof, one needs to come up with some property that would separate low-rank matrices from some property that would imply rank, right? So we come up with one. So and let me specify it. So we consider the following embedding of f2 to the n into Rn. So for any vector x, let's say non-zero, for any non-zero x in f2 to the n, I would consider a corresponding real vector, which is just normalized version of x. So it's x divided by the L2 norm of x. So this is some strange embedding of f2 to the n into Rn, into positive orthant. And then we define the following quantity. So so let's say that I have a set V in Rn, a finite set maybe. So this is our main quantity, a sub r. Well, let's say it's an f2 to the n. A sub r of V is the max for W in Rn. So this is our, yeah, so I would try to be clear about this notion. So this is the main notion that we are going to use. So let's say that I have a subset V in f2 to the n. Let's say that it doesn't include 0. Or let's say that 0 maps to 0. So this mapping is for non-zero vectors, and then 0 maps to 0. OK, so now, I often assume that this embedding is implicit. So I take my set V, I embed it into the real space using this embedding. Now I get a bunch of points in the real space. And now I try to find I look over all r-dimensional linear subspaces of Rn. And I pick one that maximizes the smallest projection from a vector V onto my linear subspace. So I want to find a space so that all of these vectors V have a large projection onto it. And I pick the one that maximizes the smallest projection. Yeah, W is a subspace. So W subspace. So it's a real subspace. So this is some quantity. So this quantity is going to be high if my vectors V if they are kind of flat. If there is a direction that they're all aligned along a linear space, then this quantity is going to be high. And if they all look in different directions, it's going to be low. So and the
So if V is the whole, if V is the entire f2 to the n, you get 0.
no. So No, let's exactly do that. So yeah, that's where it starts. So our first lemma, and I will state few lemmas, and then we will go back and prove some of them. So yeah, the first one is, yeah, so how does this quantity behave? So what is a sub r of all of f2 to the n? Well, so let's assume that r is O small of n, and then this behaves like r over n. We can prove that, or prove it a bit later. Maybe I'll state a bunch of lemmas about this, and then we'll prove some of them. So yeah, this is the behavior. So it's not going to be 0 because it's, yeah, so this is, I mean, the hardest thing to approximate in all of f to the n are the unit vectors. But then they are all in the positive orthant. So yeah, you can get some correlation with all of them. It's going to be small, but
That you take the diagonal.
well, yeah, one dimensional would be a diagonal. Higher dimensions, the approximation space would look like. So you take the coordinates, you partition them into and then. So let's prove this result. Yeah. So right. So first let's prove an upper bound. So let's prove that a sub r. A sub r of f2 to the n would have to be less than a sub r of just the unit vectors, e1 through en, right? So if I want to approximate just the unit vectors, it should only be easier than approximating all of f2 to the n. OK, so now let's say that I found some linear space W in Rn that gives me some good approximation. So it should have some bases, right? It should have some orthonormal basis, W1 through WR. So this is the orthonormal basis. Now let me consider the following sum over I in R, J in N, Wi Ej squared. So what can I say about the following sum? Well, so it really, I mean, I'm saying that this sum is going to be, in fact, exactly R. Because EJs, they form an orthonormal basis. So they don't change under embedding at all, because they're unit vectors. So for every Wi, I'm just taking the sum of projections on all of these vectors. So the sum is going to be R. So but if the sum is R, this means that there exists J in N such that the sum over I in R, Ej times Wi squared is at most R over N. So this means that, but this quantity, it's exactly the square of the projection of Ej onto W. So and we proved that it's at most R over N, so this quantity is also at most R over N. So this is an upper bound, and yeah, let's also prove the lower bound. Oh. No, I want to keep this. Yeah, so let's prove the lower bound. So I need to prove that a sub r of f2 to the n is at least, so with some small terms, it's at least n over r. So I need to specify a linear space that would give me good approximation for all of the Boolean cube after the embedding. Sorry? R over n. Yeah, sorry. Right. So okay. So here is how I pick my linear space. So I look at all n coordinates. I break them into sets of size n over r. Well, I need to write integer parts, but let me not do that. So and then I take the first vector that is ones on the first block and zeros everywhere else. So that will be my W1, and then Wi would be ones on the ith block and zeros everywhere else. So that will be Wi. So I get R vectors like that, and I claim that this is in fact an approximating space. So why is this? Well, yeah. So we just need to do the computation. So let me take an arbitrary vector v in f2 to the n, and let me look at the projection, square of the projection of v So sum over I in R VWI squared. Well, okay, so let's say that the Hamming weight of V is T, then maybe let's call it A. So then how, okay, so then how many, so then let's look, okay, so here is my vector V. So it intersects the supports of some of these block vectors. No, maybe not all of them. So let's say it intersects T of them. So the weight of V is A, and V intersects T blocks. So T is at most A, right? Okay, so so then let's say that these are the first T blocks. So then I would vary just in T. So I goes up to T, and I'm looking at a quantity like that. And also, let's have notation for all of these intersections. So it intersects the first T blocks. So let's say that the intersection with the first block. So so the support of V intersect block I is AI. Then we have sum over I at most T. AI is A. Okay, so now we can write the expression for this quantity. Well, so what is that? So what is vector V? Well, so we said that its weight is A. So in every coordinate, it would look like 1 over square root A, because it's normalized. Right. So with block number I, it has AI coordinates in common. So I get to multiply by AI, and each of the block vectors, I mean, they're also normalized. They're unit vectors, so they look like square root n over r. So right, and then I get to square this. So this is the sum that that tells me the square of the norm of the projection. Okay, so what is that? Well, right. So sum. Well, I get 1 over A here. R over n and AI squared. Right. So this is R over n over A, sum over I at most T, AI squared. Now, when is this minimized? Well, when all AIs are the same. When they are the same, they all log AI is A over T. So this, okay, A squared. So this is at most R over n A over T squared times T. And now everything should cancel. So, okay, so I lose the square and A and this T. And I get R over n A over T. And as I know, T is, there is an so T is at most A. So that's at most R over n. Sorry, so that's.
Did you want a low bound? You wanted to prove that all the.
Right, sorry. I
It's fine. Just as it's most should be at least in some.
Yeah.
That's all.
Oh.
Sum AI squared is at least.
It's at least good. Yeah, exactly. And all these are. Yeah.
Never matters which direction it was.
Yeah. Well, yeah. So so that was our first result about this measure. Right. So this is how inapproximable is all of the Boolean cube. The next thing to observe is that this combinatorial design property, in fact, shows that these matrices are in fact as hard to approximate as all of the Boolean cube, if the dimension of the approximating space is large enough. So let me state something like that. So another lemma. So let's let m be 1 over epsilon, so m is an integer. And let's say that the dimension approximating of the approximating space is high, so it's at least n to the 1 minus epsilon, omega n to the 1.
N is 1 over epsilon, or m.
M, yeah.
It's just an integer.
Yeah, m is an integer, and yeah, we'll write it as 1 over epsilon. And let's look at high dimensional approximations. So R is omega of n to the 1 minus epsilon. Then, in fact, we can prove that a sub r, I mean, and that's a fairly easy result. So it's an actually very easy result. That then these matrices Vm, they are as hard to approximate as all of the Boolean cube. Oh no, V is yeah, it's this V. So I said that. So I defined geometric designs. So these are designs with parameters m and q, and then V is it's an n by n matrix with the parameters of a geometric design.
But this AR is defined for a subset of n. So
Right. Oh, right.
set of rows or
Yeah, that's the set of rows, exactly. Yeah, you take the set of, so yeah, I apply this to matrices also. For a matrix, you just take the set of rows of the matrix, and then you compute this quantity. So that's another lemma. This follows just by spectral arguments. So I mean, you look at this matrix, you can compute the spectrum of V times V transpose. Then from there, you can get an average in approximability result. So I mean, we can prove that. But let me state a few more, and then we'll prove some of them. So so then one can prove also the stability results. So here we said that all of the Boolean cube is very hard to approximate. So here we said that if you look at high dimensional approximations, then design matrices are as hard to approximate as all of the Boolean cube. And in the next lemma, I'll say that, well, this is true even for perturbed design matrices. So even if I mean, that's kind of intuitive that this measure doesn't depend much on the perturbation. So if you perturb the matrix a bit, it's still as inapproximable as all of the Boolean cube. So so here is the general statement. Right. So let's say that I have a subset V in F2 to the n. And every row has some weight W. And then there is another subset V prime, which is obtained by which is a deperturbation of V. So this means that, well, you can think of it as a matrix. So let's say it's an, I mean, it's true for let's say it's a matrix. So it's, yeah, so it's a matrix. This is a matrix. And then, yeah, I do exactly what I did when defining rigidity. So for every row, I change this row in up to d coordinates. So I get another matrix called V prime. And now I'll relate a sub r for V to a sub r of V prime. So, and the relation is the following. So a sub r, well, assuming that d is less than w, we have a sub r of V prime is at most square root a sub r of V plus square root d over w squared. And this says what one, in a sense, would expect. So if a sub r is small and d is small compared to w, then a sub r of V prime would also be small. So if I take a collection, a matrix which is inapproximable, I perturb it a little, I change it in a small number of coordinates, the resulting matrix would still be inapproximable. And in particular, so combining the two lemmas, one can get one more. So let me state that one. And that would be the last approximability lemma that we need. Again, m is 1 over epsilon. D is n to the 1 minus 2 epsilon. R is large, so we are looking at high dimensional approximations. Then a sub r of V prime is also R over n. So so this, I mean, we're just selecting some regime where if we look, so yeah, so I take this, the design matrix corresponding to an m-dimensional projective space. I'm saying that, or a combinatorial design with the same parameters. I'm saying that if I perturb it in this reasonably small number of coordinates in every row, so n to the 1 minus 2 epsilon, well, not that small. Then if I look at r-dimensional approximations for a pretty large r, omega of n to the 1 minus epsilon, then in fact approximating this matrix is as hard as approximating all of the Boolean cube. So this this is the last statement about the last inapproximability statement. Now, so how do we want to prove rigidity? Well, we want to prove rigidity by saying that, well, so how can one go and prove that a matrix has high rank? So how do we want to prove that? Well, we want to say that, in fact, if you take a linear space, if you take an F2 linear space, then it is going to be approximable. So, and therefore, if you have a collection of vectors which are inapproximable, they cannot lie in a low-dimensional linear space, because low-dimensional F2 linear spaces are going to be approximable. This is the separation between rigid and non-rigid. Yeah. So let me. I'll just state the conjectures with a formal conjecture, yeah. So let me put it here. There exists alpha, delta, and epsilon bigger than 0. Well, again.
So you're giving some intuition before the formal conjecture. So you can do
Okay, the intuition, absolutely. Great. So this collection of lemmas that I stated here. So the main one is the last, right? So and the last one says that, well, so we have this notion of inapproximability. We say that. So what does it mean that a certain set is inapproximable? That means that approximating this set is as hard as approximating all of the Boolean cube. So this is as bad as it can get, right? So this lemma said that if I take a design and even allow myself a perturbation, a fairly strong perturbation in every row, then if I look at high-dimensional approximations, so if I'm trying to approximate it by high-dimensional space, it's going to be as hard to approximate as all of the Boolean cube. So now let's say that I have another set of vectors, another set of elements of F2 to the n that I know that admit a non-trivial approximation. So let's say, yeah, so I have some set S in F2 to the n that admits a non-trivial approximation.
that might be the counter example to the rigidity of a matrix.
Right. So I want to say that the rows of my matrix cannot be contained in a set like that, because the rows of the matrix are inapproximable, and that set is approximable. So the rows of the matrix cannot lie in that set. So if I prove that low-dimensional F2 linear spaces are approximable, this would prove that the design matrices have high rank. Because if design matrices had low rank, so I know that design matrices are inapproximable. So, but if they had low rank, then they would lie in a low-dimensional F2 linear space. But if I know that F2 linear spaces are approximable, this means that they cannot contain rows of a design matrix.
So you mean low-dimensional linear space?
Yes.
We know that full space is not approximable.
Yeah, low-dimensional F2 linear spaces.
Low has to be what, n to the 1 minus epsilon?
Low would unfortunately have to be.
Or n bigger. So
it would have to be no, small. So it would be n to the 2 epsilon plus delta. So that's how low we need. So I would say that so every F2 linear space of dimension that much has to be approximable. And if I can prove that, then I prove rigidity of design matrices. And I won't prove that, but I would prove some weaker results towards there. So let me state the conjecture formally. So there exists alpha, delta, and epsilon. So epsilon is 1 over m. So all of these are bigger than 0, such that for all linear spaces L in F2 to the n, where the dimension, and this is the usual F2 dimension of L, is at most n to the 2 epsilon plus delta, for some R which is large, there would be a non-trivial approximability result. So a sub R of L would have to be at least 1 plus alpha times R over n. So this is the main conjecture.
For some
Yeah.
So here, your design matrix are very sparse.
So
Your design matrices are very sparse.
yes.
But here you want to check almost all the entries.
almost all the entries, but it's roughly the size of an intersection of two rows.
Yes.
So what's n?
No, it's not. It's yeah. I mean, so okay, yeah. So yeah. This is. Let me write this in terms of delta, in terms of epsilon. So remember that m is 1 over epsilon. So this is. So this is n. This should be n to the 1 minus epsilon, and this is n to the 1 minus 2 epsilon. Oh, so there is some constant here, I guess. Right. So n is q to the m. So then q to the m minus 1. So then q is like n to the 1 over m. So here you are dividing by q. So 1 over m is epsilon. So you start with the design matrix. Every row has n to the 1 minus epsilon 1s. No, there is no. Sorry, there is no. Yeah, that's fine. So yeah, and the number of changes, as Avi said, yeah, it's about the size of the intersection between two rows. So yeah, the rows, they still remain pretty much. I mean, they're much heavier than the number of intersections that we allow. So this is the conjecture, and yeah, and one can prove a theorem that if the conjecture were true, if the conjecture is true, then in fact this implies that these matrices are rigid. So and now let me state. I mean, all these theorems, all these lemmas, they're easy to prove. I mean, there is nothing particularly interesting there. The more interesting results are the results that we have on actually approximating F2 linear spaces. So what we can prove is that so to a certain degree, F2 linear spaces are approximable. So you can take an F2 linear space of low dimension. You do this weird embedding into the real space, and then apparently all these vectors they are well aligned along some real space, somewhat well aligned along a real space. And a stronger result of this nature would prove rigidity. So let me state what we can prove in terms of these positive results, and then those I hope I would actually prove at least some of them. So
yeah, so you can take a break whenever you like.
Yeah.
5 or 10 minute break whenever it's convenient.
yeah, so I guess I'll state the theorems, these positive results, and then we'll have a break. Oh, so okay. So how would we measure our progress towards the conjecture? So there are quite a few parameters here, right? So so we're saying that so there are these constants such that every linear space of dimension up to so much is good. So what means good is that in some high dimension, for some high dimensional approximations, it admits a non-trivial approximation. So then how good can we do? So so the best we can do, so we cannot prove this, but if you look at somewhat lower dimension, then this is actually true, and we can prove it for all. So we can, if we replace this by O small of n to the epsilon times log n, then this is actually a theorem. So so if we are looking at low dimensional F2 linear spaces, then they do admit a non-trivial approximation. It's just that low dimension for that we can do that is too low to imply rigidity. So but on the other hand, I mean, okay, it's also polynomial. It's just that it's a different polynomial.
How would you conjecture it for square root n independent of epsilon?
Okay, sorry, can you say?
Dimension of L is root n. Do you think it's 4 or you know it's false?
Let's say, well, the whole thing. Oh, but what is R? Because R depends on. Oh, but R depends on epsilon. So it's so so I mean, so there are so you can take any dimension and you would be able to get some. So I'll state our positive results now. So you can take in. Yeah, so let me state the positive results.
Okay, let me rephrase
I don't know. So given that there is existential quantifier over epsilon, so for small epsilon, it might still be true. Yeah. So yeah, so let me state the so this is theorem 1. So for any L in f2 to the n, where the dimension of L is k, A1 of L is at least 1 over k. So that's a very short statement. So if I take a k-dimensional f2 linear space and I do this weird embedding, then in fact all the vectors are sitting in some cone. So there is a one-dimensional real space, so that all of them would have high projection onto that real space. And that's in sharp contrast with what I would get for f2 to the n, right? So there is a huge separation between L and the whole of f2 to the n, because for f2 to the n, we know that A1 of f2 to the n is in fact 1 over n. Well, it's in fact exactly 1 over n. So there is a vast, vast gap between low-dimensional f2 linear spaces and all of the Boolean cube. Because again, for us, k, like we are thinking of like this n to the, well, let's say 2 epsilon plus delta, or n to the epsilon. So it's polynomially low. There's a huge gap in approximability. And and that alone, in fact, is already proves the conjecture. So for all linear spaces of dimension up to n to the epsilon, by just using one-dimensional approximations, given that one-dimensional approximations for f2 linear spaces are so good, I can say that, well, so then I would, so if somebody gives me a low-dimensional f2 linear space, so if somebody gives me a linear space of dimension up to n to the epsilon, then I know that there is in fact a one-dimensional approximation that is already better. I mean, so I'm beating this factor r over n for all r up to n to the 1 minus epsilon. So it's like I'm allowed to look at these high-dimensional approximations, but I just have a one-dimensional approximation, which is so good I don't know what to do with other dimensions. But this one-dimensional approximation is already so good that it allows me to get that far.
But it's a lower bound here. So what good approximation is this?
Oh, sorry, did I put the upper bound? It should be. Sorry. No, that is a lower bound. That's correct, and that one is also a lower bound. No, that's fine.
So no, I mean, talking about your terminology.
Mm-hmm.
It's a good embedding when this is higher.
Yeah, it's
Okay, good.
yeah. So yeah, let me state the second one, and then we'll have a break. So for all L in f2 to the n, so, well, basically, the first result says that if I just look at one-dimensional approximations, then I can already get this factor of 1 over k. Now, one would hope that allowing ourselves higher dimensional approximations, we should be able to grow also the approximation factor. So that's what we do in the second theorem. Unfortunately, the growth is very slow. So we can go to polynomial dimension of approximating space, so like n to the tau for any tau, and then we can get another factor of log k. So we rather than from 1 over k, we go to log k over k. So yeah, and that proves the conjecture for all spaces of dimension up to n to the epsilon log n. No. Well, because there are also changes that you have to well, it gives you, so for Hamada conjecture you can get some implications from here, but also pretty weak ones. So you can, so for Hamada conjecture you can ask, so okay, so you look at this matrices VM, so what can you prove about their rank? So Hamada conjecture says that the rank has to be at least this much. The rank over any field has to be at least this much, because the rank has to be at least what you get for geometric designs. So what can one prove? So the trivial lower bound on the rank would be n to the 1 over m. So using these results, but in fact this can have a simple proof. You can prove some things like n to the 1 over m log n. So for rigidity, no. I mean, if well, yeah. So you have this term, right? So yeah. I mean, yeah. I don't think that it happens. Let's have a break, and then I'll go into the theorems.
Well, it's out of time. He asked me for the paper.
Yeah. So Kolmogorov width is a quantity which is in fact equivalent to our notion a sub r of v. So let's say that v is a subset of Rn. So then okay. So I have this subset. So this is my subset. Maybe it's a finite subset. So this is my set of points in Rn. And then I'm trying to find an r-dimensional real space that minimizes the distance of every point to that linear space, that minimizes the largest distance of a point to a linear space. So that minimum of the largest distance over all r-dimensional spaces is called the Kolmogorov width of a set. So and this is the identity. So Kolmogorov width is just the 1 minus the square root of our r of v. So we are talking about maximizing the projection, and Kolmogorov talked about minimizing the distance, but these are obviously the same. So the title Kolmogorov width of discrete linear spaces, so we take an F2 linear space, we embed it, but then we talk about a quantity which is equivalent to Kolmogorov width. So all our conjectures can be phrased in terms of Kolmogorov width. We talk about projections, but that's the same thing. And yeah, so in I don't know, in functional analysis, maybe in some other areas of mathematics, this Kolmogorov width is used a lot. Great. So let me get onto proving the positive results.
One thing is not clear to me about the conclusion. If you prove a lower bound on A1,
Mm-hmm.
why do you get it? You wanted the lower bound for R, which is much bigger than 1, so why does it follow?
Right. So it's true that AR is large. AR of any set V is larger than AR prime for V if R is larger than R prime, right? Because if you log, yeah, it's so that's it. Yeah. Okay, so let us prove this first theorem. So I have an k-dimensional subspace of f2 to the n. I do this weird embedding into the real space, and now I want to prove that in fact all these vectors are going to sit in a small cone. So there is going to be some one-dimensional vector, unit vector, so that all of them have a large dot product with that vector. So proof of theorem 1. So first, let me define the following quantities. So for every I in n, I define W sub I to be the maximum over all V in L, such that I is in the support of V of the Hamming weight of V. So W sub I. So I have these n coordinates. I fix some coordinate I, and I look at all vectors that have this coordinate in their support. Vectors in L that have this coordinate in their support. I take the smallest one. Sorry, I take the smallest one. So I take the vector of the smallest weight that contains this coordinate. So and that is my W sub I. So if there is no such vector, so if some coordinate is never used, then I would call this to be infinity. So minimum or empty set it would be infinite. Then I define the following measure, mu of L. It's the sum over I in n, wi inverse. So it's some characteristic of a linear space. So I sum over all coordinates of inverses of this w sub i's. And now I'll just guess. So I need to guess a good one-dimensional approximation for my linear space L after the embedding. So I would guess it. So I would take a vector x in Rn that looks like the following: 1 over square root mu wi. So this is a vector in Rn. Yeah. So this is how it looks. So in coordinate number I put 1 over square root mu w sub I. So it's some vector. So what can we say about that? So first, let's observe that this is in fact a unit vector. So the L2 norm of x is the sum over I in n of squares of this. But what? So it's mu wi. Well, but that's in fact 1 over mu times mu. This is 1. So then the L2 norm of x is 1, pretty much by definition. So and now all I need to show is that in fact for any v in L, the dot product of x and v, well, I would be very happy if I could show that it's at least 1 over k, right? If I could show that it's at least 1 over k, then that will prove my bound, because I need to prove that the square is at least 1 over k squared. So let's try to prove some lower bound. So what can we say about this product? Well, it's the sum over all I in the support of v, 1 over square root mu wi times, well, what do we have in v? Well, it's 1 over, let's say square root w. So let's say that w is the Hamming weight of v. So then I put here 1 over square root w. And is that it? Sorry. So 1 over.
Are you going to use only the term from this sum that comes from I?
Sorry.
You want a low bound. Are you going to use only the ith term in this sum?
No. No. So I'm going to use all terms, all of them. Yeah. So right. So I varies in the support of my vector v. Yeah. And then for every I get the following quantity. Yeah. Good. So.
I'm not sure actually what Avi's question was. What is the ith term?
No, I also am not sure I follow. So I varies overall. I runs over all the support of v.
I just wondered if you'll get the low bound just by looking at the ith term.
No. Yeah. So I'm looking at the whole sum. So
no. From the support, there is the ith term and other non-zero term. The ith term contributes something, and the others contribute something else.
Yeah.
They may be much smaller, but okay.
Yeah. So here is one observation. So in fact, for every I, there is a relation between this wi and w. So in fact, for every I that I have in the sum, wi is at most w.
Also, you are using all the elements from the support that
Yeah.
That are in w.
Yes, I'm using.
You're using w terms.
I'm using w terms. Yeah. So this is the sum over w elements. Yeah. So and I know that for every I, wi is at most w, just by this definition. So then the sum would only become less if I replace
All the wi's in this part by w. So you first do the sum only on the support of v. You restrict yourself to the support. Sorry, you are on the support of v.
yeah, I am on the support.
You are going to replace every wi by w.
Yeah. So a second, I want to convince myself I want to do that. So.
You just get 1 over square root mu.
That will be small.
Oh, sorry. I'm not trying to prove a lower bound. I'm trying to. No. I want to prove. Sorry, 1 second. Oh yeah, good. Yeah, no, that's all correct. Yeah, I'm replacing it by W. Yeah, you're right. So right. So then what do I have? Well, I will get. So I'm summing W terms. So it's W times 1 over square root mu, well, times W times square root W. And that's exactly 1 over square root mu. Good. So now if I had an inequality that, so but I don't want square root mu. Well, I want 1 over square root k. So if I could prove that mu is at most k, then I will be happy. And that's exactly what I will prove now. So right. So how do I prove that this strange quantity mu is always upper bounded by k? So that's another lemma. Mu of L never exceeds the k, the dimension. So I consider the following hypergraph. So there are n nodes. So the nodes are n, so 1 to up to n, correspond to coordinates. So nodes are coordinates. And edges, hyperedges, are supports of elements in L. So if there is an element in L, then I take its support and I put a hyperedge. So this is some hypergraph. And also for every node I know that there is this quantity Wi associated with it. So what is Wi? So that's just the size of the smallest hyperedge that contains that node. So okay. So and now I do the following. I run the following. So I also would have a potential function. So originally the potential function set to 0, and I color all nodes. Color all nodes white. And then I do the following. I run the following procedure. So I pick the pick a white node with the smallest Wi. So okay, so if I picked I picked a white node with the smallest Wi, well, so there ought to be a hyperedge of. So there is a corresponding hyperedge E sub I, and the size of E sub I is Wi. So then I add this edge to the list. So remember, E sub I, color all nodes in E sub I black. Well, I will also change the potential function. So phi. So basically, yeah. So phi keeps track. Okay. So every node has W sub I associated with it, and let's say that it also has the weight. So well, there is this quantity 1 over W sub sub I that is like the weight of this node. So and then the.
Let me just, for intuitions, for what you're going to do, you're going to somehow show that if it was bigger than k, you can find more than k independent.
Exactly.
Yeah, and the vectors will come from subsets of supports of this.
Exactly.
Okay.
Yeah. So that's exactly what I'm doing. So phi tracks black weight. So right. So basically, yeah. So I will get a contradiction. Well, yeah. So yeah. So I will say that either mu sub L should be at most k, or if it's higher than k, then I will be able to build a tower of more than k linearly independent vectors. So
In fact, they'll be disjoint.
no, disjoint.
They're triangular. I mean,
Yeah,
so-
triangular, about triangular. Yeah. So yeah, and the way I'm doing that is, yeah, I'm building this hypergraph, and then color the nodes white, and I have the potential function that keeps track of the weight of black nodes. So originally it's 0. Then I do the following iterations. So I take the node with the smallest value of wi. I take the hyperedge that gives it this weight wi. I add this hyperedge to my set. I mean, it expands the support of all edges that I picked so far, because I'm adding a white node, and I'm changing and then I color all the nodes that are in this hyperedge black, and I adjust the weight, the value of the potential function accordingly. And and one can see that I'm adjusting it by less than 1, or by at most 1. So it would take me, if mu sub L, and in the end I would get the value of mu sub L. So if the value would be larger than k, then I would have to do more than k steps, and that would give me a contradiction. So this is the whole argument. So therefore mu is at most k, and therefore we get this good one-dimensional approximations. Right, and also as Avi pointed out, so this in fact applies not just to linear spaces, but to all sets of bounded triangular rank. So in fact, our second theorem also applies to all sets of bounded triangular rank. So we have some other results that do use more fine-grained structure of linear spaces, but they are more specialized. So we can say that for certain particular kinds of linear spaces, like cut spaces. So a cut space is a linear space that has a generator matrix where every column has weight 2. Say for these ones, we can in fact prove the conjecture, and there the argument uses more than just the height. But the general results, they are just based on the triangular rank, which is a weakness, but that's where we are. Good. So yeah, so this.
This argument is tight, right? For which the subspace was spanned by unit vectors.
Yeah. Then that's it. Yeah. Right. So this gives us this strong one-dimensional approximations, and now, yeah. So now the question. But we don't. I mean, so these one-dimensional approximations are really, really good. They separate us from the whole Boolean cube. I mean, in the end, yeah. So what is this conjecture saying? It says that approximating a low-dimensional left linear space is easier than approximating all of the Boolean cube. And we need this statement for pretty high dimension. We need this statement for pretty large values of R. So this theorem says that if we look at low-dimensional approximations, one-dimensional approximations, then the separation is vast. It's way, way easier to approximate low-dimensional left linear spaces than all of the Boolean cube. So we need similar results for higher dimensions. So in the next theorem would be like that. So we would look at higher dimensions. We would be able to improve our approximation factor, but not by as much as we would want.
So for dimension n/2, you get a factor of 2 approximation in this.
For
dimension of L, let's say n/2, for example.
Yeah.
And one-dimensional approximation, you get a factor of 2.
Yeah. Yeah.
And you only need a gap of 1.001.
But I need that gap. So
you need this gap for high-dimensional approximation.
Well, no, I don't need this right. I need it for high-dimensional approximations, but I don't need the dimension of L to be as high as n/2. The dimension of L can be polynomially low, and the gap can be arbitrarily small, but I need a multiplicative gap. Yeah. So now let's go into that more general. So into high-dimensional approximations. I'll have to sacrifice something. What dream version? Well, I mean, to begin with, I would want that. So yeah, so let's say that, yeah. I mean, so put root k here. Let's say. I mean, that would probably already be enough. I wouldn't. I mean, yeah, most likely that would already be enough. So I mean, but then you don't need to do n to the tau. You can do. Well, you can put something like n/k here. So you can go to much higher dimension of approximating space, but you need to improve this factor. So you don't need you are not happy with 1 over k. You want to grow this. Yeah, it's hard to map between parameters here and there. There are too many. But yeah, so basically, yeah, so you want to you can sacrifice the dimension. You can grow the dimension further, but you want to improve the approximation factor, and you want to improve it by more than polylogs. I mean, even if you could do log squared, I think that would be. I mean, that would certainly be progress in the Hamada conjecture. So in fact, improving log by anything would be a good progress in Hamada conjecture. To get rigidity, you need to get polynomial factors, and moreover, not arbitrary. So most likely, so maybe it should be even half minus epsilon. So. So before I go into the proof, so that proof is longer and more technical. So let me give one definition. So first, also, so let me make one observation about this measure a sub r of L. So what is? I mean, it's a strange embedding, right? So we take this F2 linear space, and then we are putting it into the real space, and then we talk about that. So, but in reality, I mean, so what is? So if one wants to prove, like, so first, I mean, the only vectors which are hard to approximate are the ones that have low weight in an F2 linear space. Because if a vector has high weight, right? So let's say that I look at a linear space L in F2 to the n, and the dimension of L is k, and let's say that I'm just interested in proving a bound. So I want to a sub t of L. I want to show that it's. I mean, I just want to improve upon the theorem 1, so maybe even just by some constant. So I want to improve this 1 over k by something. So I want to get a better approximation factor. So maybe I want to get c over k. So and I'm fine with drawing the dimension. So I want to say that if my vectors, so for every vector v in L, such that the Hamming weight of v is large, so well, somewhat large. So let's say it's above some alpha times. Well, so it's above some alpha times n over k for alpha bigger than 1, then in fact that comes trivial. Because why? Because, well, then I can just, since I have this t which is no longer 1, so I don't have to pay for increasing the dimension, say, by 1. So I can just add, I can just take the all ones vector. So 1 over root n, 1 over root n. So this is a vector in Rn. And I say just this single vector would already have high dot product with v after the embedding. So because what is that going to be? Well, if so let's say that the weight of v is w, then this dot product is v times this all ones. Well, so this is going to be w times square root w times 1 over root n, so which is root w over n, which for when in the case when w is alpha times n over k, so that would give us so this is alpha times n over k. So it would already give us square root alpha over square root k. So I'm already improving upon, so as I said, so if alpha is bigger than 1, so if the weight of my vector is notably above n over k, then it's trivial to approximate it. It's only the low weight vectors in F2 dimensional linear spaces that are hard to approximate.
Square root of k. Oh, you square it then.
Yeah, because, and then I have to square it.
So basically, I guess alpha is c.
Yeah, alpha is c, or alpha is c. I could have called that this. Yeah. So yeah, one thing that this embedding of F2 to the n into Rn that it does for you, it takes care of all vectors whose weight is somewhat high. So if the weight of an F2 vector is higher than some threshold, then you really don't care about where it goes. It's the low ones that you have trouble approximating, and that's always the problem with rigidity. I mean, if you're trying to prove rigidity of a design matrix, you're fighting with low weight vectors in an F2 linear space. So. Right, so this motivates the next definition that I'm going to give. Okay, so let's say that we have L in f2 to the n. The dimension of L is k. And S is a subset of n. We say that S is a C comma K attractor for L if for all vectors V in L such that the support of V intersects S is non-empty, we have, it is somewhat large. So support of V intersect S is at least C times size of S over K. So the intuition is that, so I have, well, so what is an attractor, right? So I have this linear space L. I only care about the supports of its code words. So there are all the supports sitting around. And then I say that some subset of coordinates is an attractor if it has the following property. If some vector, if some code word touches it, so if it intersects its support, then in fact it intersects it by a lot. So if you touch it, then you touch it a lot, so it attracts you. So that's the name where the name attractor comes from. And then, okay, so then also why is a lot defined this way? Well, yeah, because in reality we only care about low weight vectors in L, and low weight vectors in L, well, they so okay, how low? So let's say that their size is close to n over k. So that's where we are playing. So it's like sampling every coordinate of. So what is a vector of size n over k? Well, I can think of it, if I could have some random model for it, it's like sampling every coordinate with probability 1 over k. So for a set of size S, how many coordinates would I expect to sample? Well, it should be S over k. But here I'm getting more by a factor of c. So this is an attractor. So a set as an attractor.
But didn't you say that you can assume that it's only bigger than c times n? Just from the previous argument, you needed this c in the Hamming weight of the vector.
Well, then there I said that if I have a vector which is of high weight, then I don't really care what happens to it at all, because I can approximate all these by a single one-dimensional vector.
Yeah, so you have to, I see, so you have to do it for vectors of Hamming weight less than c times n over k.
Right, but here I'm saying I'm defining. I take just all of them. So I really don't care about the big ones, but I would be able to construct attractors, in fact, for the whole space. So and yeah, this is my definition of an attractor. So if a vector touches you, then it should touch you a lot. And so one thing to observe is that this definition, it's trivial to satisfy it with small attractors. In fact, if I take just a coordinate, so if I take just a set which has a single coordinate, so this is my, so this is a very strong attractor. This is in fact a KK attractor, because if some vector touches it, well, then the intersection of the support, well, it's at least it's exactly 1, in fact, because it's one coordinate. But one, I mean, one is, so you have to put C to be roughly K. So it's a pretty strong attractor. But what we'll prove is that in low-dimensional F2 linear spaces, there are large attractors which are somewhat strong. So this is our and that's non-obvious and maybe somewhat surprising. But in fact, if you look at a low-dimensional linear space, then there are going to be large subsets of coordinates where if some low weight vector touches that subset, then it actually has a lot of weight on that subset. So here is our main lemma about attractors. again, so L is a subset of f2 to the n. Dimension of L is k. And let's say that we restrict our attention to the supports of L. So L is a union over V in L of supports of V. So we remove the coordinates that don't carry any, that do not support anything in L. So we also make an assumption. So assume, well, let me not put the dimensional, let me honestly write triangular rank. So because it applies to all sets of bounded triangular rank. So assume that for every V in L, the weight, so the weights are somewhat close. So the weight of V is between some W and 2W. There is one more technical assumption about constants. So So I take a linear, well, I take a set of bounded triangular rank, or I can say that I take a linear space of dimension k, but then I restrict my attention to some slice of it. So I look at all vectors whose weight is in the range between w and 2w for some w. So I'm not looking at all the linear space, but I look at the portion of the linear space. And I take the union of the supports of all these vectors. So this is some set M, and I claim that there is going to be a c comma k attractor of fairly large size, of size n over 2 to the 4c. So there is some dependency on constants, but so there is going to be an attractor. In fact, as long as c is below log n, there is going to be an attractor which is large. So and if c is a constant, and in fact I can take a constant fraction of coordinates. And I would have this behavior that all low weight vectors that touch that set of coordinates actually touch it by much more than one would expect. So yeah, so I'll try to prove this lemma. So we only have like about 20 minutes remaining. This is the most interesting technical lemma in the whole paper. So then from here, let me say just a few words. So how does one actually go to constructing approximating real spaces? So once you have attractors, you do something similar to what we did. Well, you are trying to partition coordinates into attractors. So and you cannot quite do that, but you can come close to that. So and if you could partition coordinates into attractors, then for every attractor you would take a vector whose support is that attractor. You put ones in everywhere on the support, and that happens to be a good approximating real space. But yeah, let's try to prove this lemma about existence of attractors.
So let me just ask you, your support, the good approximating subspace will be spanned by disjoint,
Yeah.
by vectors with disjoint support.
Yes.
So in this case, if you only restricted yourself to this kind of subspaces, can you beat this result?
I don't know. Oh, can you prove existence of larger attractors?
Can you do better than log k over k, which you get? I mean, maybe it's too weak to get the result you want about approximating.
Oh, you're saying that.
If you restrict yourself to real subspaces spanned by vectors with disjoint support.
But then, so your question is whether I can improve what?
Whether you can, prove rigidity this way, just by restricting yourself to this type of subspaces.
Well, but then I need to look at these inapproximability results also, right? And
yeah, no, so you restricted. I mean, you reduce the problem of proving a rigidity result to proving a good approximation
Yeah.
result for linear subspaces of low dimension.
Yeah.
And now you're looking for this good approximation.
Right.
Right. You can look for it anywhere, but you decide to restrict yourself to real subspaces whose spanning set
Right.
can be set with disjoint support.
Right.
Will this even potentially possible to use to prove rigidity this way?
I don't know. I don't know. Maybe not. But but this one-dimensional space that we constructed, that one was not of this type. So that one actually had different weights on different. I mean, that it's
It's one vector.
it's one vector. Yeah. Well, it's one vector, but you have different numbers and different coordinates, right? So it's.
Yeah, so I'm asking. Yeah.
But here also you take the one vector and this contraction matrix. So
Yeah, so I don't know the answer to that one. We have some other results that where we don't do that. So, but on the other hand, they don't go to dimensions as high. So, like we know how to construct three-dimensional. So let me just mention that. So if you there is a gap, right? So because there you just do one-dimensional approximations, and then I jump all the way to like this n to the tau. So I mean we had some. We even didn't write that down, but we have some theorems talking about what happens in dimension 2 and in dimension 3. So if you allow yourself three-dimensional approximations, then you can improve 1 over k. I mean, you can replace 1 by, say, 1.01. So in 3 dimensions. And there, the approximation spaces that we construct, they're not of this ladder type. So they really, so every vector there would have some, I mean, the supports are not disjoint.
But suppose you just wanted 1 over root k. Instead of log k over k, you wanted 1 over root k in any way. Not necessarily via attractors. Is it possible that you can get this kind of thing with subspaces then by disjoint?
I don't know. I don't know the answer to this. Yeah. Yeah. Okay, so let's start with some simple observation. So our goal is to construct an attractor, right? So we start with a simple observation. So we know that if n over 2 to the 4c plus 2 is below w, so just setting up some notation almost. So saying if w is very large, then in fact the whole set n is an attractor. Is an appropriate attractor. Is an CK. So I mean, and this is just computation. You plug in all the numbers, and you would. So we can without loss of generality, we assume that w is small, is below this. And then we execute the following algorithm. So we had an algorithm on that slide. So we.
Let me stop you again. I mean, just for intuition. Suppose that w is 1, so they are just unit vectors. Is it trivial to see that factor, or just? That should be a really easy case.
That should be really.
They're all unit vectors.
Well, but then you have it more.
The span is k. You probably take all of.
I would just take one of them, or all of. No, I would take one of them. I would take.
You cannot take one of them because you need a set of large size.
Why don't you take the complement?
Let's take all. So let's see. So yeah, it's a good question. So okay, so you are saying that. So I have this E1 through EK.
Yeah.
Right, and then you're asking. So what is the attractor for? Yeah. So would taking all of them work? So right. So I take this set, and now I try to.
But then you get exactly what you expect of them.
Exactly what do you expect?
The intersection of the support and S would be.
Yeah. Right. You will get 1 over k.
So it's not bigger than.
Okay. So. Oh, but I can take less, right? I can take as much less as I want. So in particular, can I take just one of them? So let me take one of them.
I thought you wanted S to be bigger.
Right. You wanted to. So I take it in the So I hit the point where I want that, and that should be fine because there it's a constant of 2 to the 4c, and there it's a c. So it should be fine. So right. So okay, so we make it an assumption. So W is small, and then we execute the following procedure. So right. So I have these n coordinates, with capital N coordinates, and I start and I'm always looking at the coordinates that remain, that I have not yet consumed. So originally, there is this remaining set R. So originally, all coordinates are non-consumed. So R is equal to N. And I start executing the following procedure. So so let's say that let's say that I have been running it for a while, and maybe I consumed all of these coordinates. So all of these are consumed. So then I pick a vector V, which that enters the non-consumed so R are the non-consumed. Right. So so on each step, so yeah, let me say what I'm doing. So I have these n coordinates, and there are these support vectors. So there are these vectors V and L, and their supports live on these n coordinates. So I am going to try to build a tower of these vectors, like what I was doing there. I will be picking these vectors one by one, extending the support that I already have, and all of them are going to be linearly independent. So eventually, I will have to halt, right? So and while I do that, I follow some strategy. So I keep track of the vectors that of the coordinates that I have not yet consumed. So this is what I call R. So originally R is all of n, and then once I start building my tower, I consume more and more coordinates. So R keeps shrinking, and my tower keeps growing. So because every time I add a new vector to the tower, I only consider vectors that have something on this non-consumed part. And I always pick the vector that minimizes the quantity that has the smallest intersection with this unconsumed part. So I'm doing a simple greedy procedure. So I want to build the highest tower. First, I take the smallest vector. Then I take the vector that is the smallest on what remains, on the coordinates that are not consumed, and then I keep doing that. So I can make at most k steps like this. And so this is some process. It will terminate after most k steps. So now I will partition the steps into stages. So there will be steps and stages. So what is a stage? So a step of the algorithm falls in the stage stage number I if at the beginning of the step. We have remaining set R sitting in between n over 2 to the I minus 1 and n over 2 to the I. So the remaining set keeps shrinking, and if it so happens that the remaining set falls in between these two quantities, then these are the steps that, if in the beginning of the step that's the size of the remaining set, then the step falls into stage number I. And let's consider the first four C stages. So at one of these stages, at some stage number I, so there exists some I among these four C stages, such that at stage I, tower grows by at most k over 4c, right? So because overall it can grow by at most k, so among the first 4c stages, there would be a stage when it doesn't grow much. So let's see. So now we'll restrict our attention to that stage I. So first, how much can the
What is the size of the set you have? You are building S, right?
I'm building. So what is it?
You're building the attractor.
No, I'll discover an attractor at some point. I'm building a tower. So.
What does the tower do?
Oh, right. A tower. So it's like a triangular rank thing. So a tower is a sequence of elements of L, where every next element extends the support of the union of the previous ones.
Just keep this set of vectors.
Right. So here is how the argument would go. So I will say that here is something that ought to happen. So there is this process. So there is this universe of size n, and there is this greedy process that is running. So first I take the smallest vector b, then I take the smallest one, but only with respect to what remains. So the one that looks out here just a little bit. And I proceed. So I'm saying that there ought to be a point where so let's say this would be the remaining side, and there ought to be a point where I would have to eat up a lot into it. Because if every time I grow, every time I add the next vector to the tower, if I every time add a little bit, then the tower would be too high. So there ought to be a point. Yeah, so the tower would be too high, and therefore the triangular rank would be too high. So there ought to be a point where where the vector that I would be adding would be eating a lot into what remains. But then this means that what remains is an attractor, because that means that what remains has the property that whatever touches it by a lot, and that's how I would discover an attractor. So that's the I probably won't be able to go through all inequalities. I'll go through some of them, but this is the intuition. So if so basically, yeah. So if every time I do that, I get as much. If every time I'm adding a vector, I only shrink the remaining part by a little, then the tower will be too high. So there ought to be a moment where I eat a lot from the remaining side. But if I eat a lot, then that means that set is an attractor, because whatever touches it, it's a lot from it. So. Right. So okay. So we partition the steps of the algorithm into stages. We said that there is one stage where the tower doesn't grow much, where the tower grows by at most something. Then we look at how much does the set R change during that stage. So let S. So S is a subset of n. So this is the change in R during stage I. So what can we say about the change? Well, say that size of S is at least n 2 to the I minus 1 minus 2w minus n over 2 to the I. And that one can in fact prove to be at least n over 2 to the I plus 1. So okay, so how does one get these inequalities? So S is the total change. So this is a set. It's the total change of the size of R at stage I. So we know that at the beginning of stage I, just by definition, the size of R, well, it has to be below n to the I minus 1. But at the previous stage, we might have eaten into it by at most 2w, because all our sets are bounded in size. So this is the lower bound on the size at the beginning of the stage, that's an upper bound on this on the size in the end of the stage. So so given what we know about W, one can get that bound. So this is how much the set S changes during stage I. Okay, so now let's look at all the steps at stage I. So let's say that there are so steps A, A1, and so on up to A plus t minus 1 are the steps at stage I. So then, well, also let delta J be the change in R on step J. So then if we look at the sum, so if we look at all steps at stage I, then the sum of their changes that we see on each of the steps should amount to the change that we see during the whole stage. So sum J goes from A to A plus t minus 1 of delta J should be the size of S, which is at least n over 2 to the I plus 1. So so I'm saying, yeah, if I look at stage I, if I sum over all the steps during the stage, then the sum of the changes should be the change during the whole stage. So, and again, just by averaging, therefore, there exists a step such that delta J, so the change at that step, is at least n over 2 to the I plus 1 times 4c over k. Because we know that there are at most so many steps at the stage, but the total change at the stage is so much. So by averaging, there is a step where the change is at least that much. But on the other hand, okay. So now so here we come to the attractor. So now let A be the size of R at the beginning of step J. So then, because we are at stage I, we have the inequality that A is at most n to 2 to the I minus 1. But on the other hand, at step J, so A is somewhat small, but on the other hand, at step J, we are eating out so much out of it. And at every stage, we are taking a vector which has the smallest intersection with what remains. So and this already shows that A is an attractor. So why is that? Well, because if we take the ratio of size of A to delta J, then this ratio, just by combining these two inequalities, so for A we have an upper bound, for delta we have a lower bound, divide one by the other, we conclude that this is at least k over c. And therefore, for any vector v in L, such that v intersect A is non-empty, the size of v intersect A is at least c times the size of A over k. So and therefore it's an attractor. And the lower bound on the size comes just from these the lower bound on the size of A. So A, we discovered it during one of the stages. We are only looking at the first 4c stages. So even at the last stage, the size of R in the end would be at least n over 2 to the 4c. So the size of A has to be large. So
A is the size. What is really A? So you switch. I mean, that attractor became A and S was something else.
Oh no, no, S was never an attractor. S is the total change during the stage. So A is an attractor.
The definition of attractor was S.
Oh, it was S. Oh, that.
S is a change in R. So it's how much you consume in the ith stage.
Yes.
And A was just the.
A,
what was A?
Oh,
was
A.
just the sum.
A.
No, but what's the definition of A?
Right. So I'm looking at stage. I pick the stage I. This is the stage where there isn't too much growth during the stage. So now during that stage, I pick one of the steps, and I pick the step where the growth is the largest during that stage. So I pick the stage where there isn't many steps, and out of these steps, I pick the largest step. So now I look at what remains at the beginning of that large step.
At the beginning of it.
And that is what I call A. So A is what remains before I make a large step at a stage where there isn't much growth.
So, but you want to show that the intersection will be large for any subsequent J, right?
No, I want to show. No, the further steps might become smaller again.
So, but the important for an attractor is the size of the intersection with A of every vector that intersects.
Exactly.
But you pick the vector that minimizes the intersection. So if this vector has large intersection,
Then every other one has also large intersection. Because that's how, that's what you were all saying. That's how this process goes. So on every step, I have what remains, and then I take the vector that minimizes the intersection with what remains.
Okay.
So if at that step if that step is large, that means that every vector is in fact has a large intersection with the attractor.